All right, we're at section 16.6, sound waves. A little introduction on in this initial image. Image is called his master's voice, and it was the logo for the Victor Talking Machine Corporation, later to be acquired by RCA Records, or at the time it was RCA Victor, since it was the Victor Talking Machine Corporation. Uh, RCA, which is Radio Corporation of America, they acquired it, and it became RCA Victor, and eventually became RCA Records. The little dog is named Nipper, and the claim is that it's the gramophone, which is shown here, reproduced the his master's voice uh, so well that he was able to recognize his master's voice. Anyway, so he's listening to sound waves coming from the gramophone. And there's three types of waves: audible waves, infrasonic waves, and ultrasonic waves. Audible waves are what you and I hear. They're in the range from, uh, you know, some people say 20 hertz. I don't know anybody that can hear that low, but low frequency, certainly 60 hertz, 40 hertz to 20,000 hertz. And individuals vary. I cut off at about 14,000. I don't go up to 20K. I lost my high register hearing a while back. And some people can hear that high, but those are audible waves, typically considered from 20 hertz to 20 kilohertz. There's infrasonic waves. Infrasonic waves are below those waves. The claim is that elephants can, when there's a thunderstorm, elephants can hear the rumblings that come from a thunderstorm, and they can turn in the direction, and so they head to where a thunderstorm is, because that's a water source, and the elephants will head to that direction, in the direction of the thunderstorm. And then there's ultrasonic waves, which are much higher than 20 kilohertz, and the typical dog whistle would be in that range. And ultrasonic waves are used in medical procedures. Ultrasound. They can look at developing baby in a mother's womb using ultrasound. Um, so the often they can tell the sex of the child just from the ultrasonic waves, and it's used for others. They look at the carotid arteries using ultrasound. We used to use it for looking at the integrity of concrete. You can detect cracks in concrete um, when you send out an ultrasonic pulse, and you expect a reflection back from the backside of the concrete, uh, knowing the physics of it. And if you get a return too early, it may indicate a crack. They inspect bridge beams using ultrasonic. So there's many scientific and medical applications for um, ultrasonic waves. Okay, let's. What is sound? You can envision here a piston. Before the piston is moves, the gas is undisturbed. So when the piston moves to the right, the gas is compressed by the motion of the piston. When the piston stops, the compression pulse continues through the gas. And so the sound wave is a compression and rarefaction of air molecules, or whatever the medium is. In if it's underwater, then you have the compression and rarefaction of the water molecules, and we'll learn that the speed of sound varies with the medium that it's in, not only with the medium but with the temperature. We'll have an equation for uh, the uh, speed of sound. We'll have an equation for the speed of sound based on temperature. Okay, so here is the repeated uh, the repeated compression and rarefaction. You can see these waves. This is a compression. This is a rarefaction, compression, rarefaction, compression. So you have this compression and rarefaction of air molecules, and it's that compression and rarefaction that gets to your ears, and your ear and brain interpret it as sound. Now, if you have more, let's say you have two people talking in a room, uh, you get a superposition of those waves. In other words, you don't have one set of air molecules being compressed and reaching you from one area, and another set of molecules being compressed as they go out in a waveform. They superimpose one on another, and they add, and you get the sound of both voices. Or the same with music. I mean, if you have a trumpet and a drum and a guitar, you're not getting individual waves. That you're going to get a superposition of all the waves merged together. Um, okay, let's look. They hear the they're using S, X of T as opposed to Y, because if you'll notice, the compression and rarefaction is in the direction of X. A transverse wave, it would be Y X of T, but since Y is perpendicular to X, and this is not, they're using S X of T is equal to S max times the cosine of KX minus omega T. And K is the wave number, X is the position, and of course, omega is the angular velocity, and T is the time. So S max is the displacement amplitude. That's we've looked at other equations, that would be our A in similar equations. And we can also look at it, we can look at the displacement of the air molecules. We can also look at the pressure, the change in pressure. The maximum pressure is sine. Notice it's sine in the displacement, it's cosine, and the pressure, it's sine kx minus omega t. And so delta P max is the pressure amplitude. Um, so here we look at the volume of I. The undisturbed gas is the area of the cross-sectional area of the pipe times delta X. And then as we, let me minimize that so there's no, it doesn't cover anything. Delta V is equal to A delta S, where delta S is equal to S1 minus S2. You can see S1 here and S2 there. And so now let's go back to thinking of the bulk modulus. The delta P is equal to the negative of the bulk modulus times the change of volume over the initial volume. And well, if the volume is equal to A delta X, then the pressure is equal to the negative of the bulk modulus times A delta S over A delta X. And of course, the A's cancel. So you can see the delta P is equal to minus B, the partial of S over the partial of X. So delta P is equal to the going back to this equation at the bottom. Oops. In the blue box, delta P equals delta P max sine kx minus omega t. We're going to move forward from there, and delta P is equal to minus B partial of that equation, S max cosine kx minus omega t, partial of x, and you end up with B, the bulk modulus S max times K sine x minus omega t. And so the pressure max is equal to the bulk modulus times S max times K. And there's a phase difference in the displacement and the pressure. You can see that the S equation, S max cosine kx minus omega t, and the pressure is Bs B S max K sine KX minus omega T. And so um, the you see there's a 90-degree shift when the pressure is at zero. Now, you have to understand that this pressure is an offset from, you can't think of this as a zero. This is this might be like 990 uh, or I'm sorry, 99,000 pascals, and this might be 101 pascals. So it's a change in pressure. This isn't necessarily a zero. So you have a change in pressure that's all positive, but when the pressure is at its uh, quiescent point, the S is max, the distance is max. And when this is at its quiescent point, the pressure is max. And you can see that there's a phase difference. And you can tell that from the cosine and the sine. Okay, now let's do a little quiz. If you blow across the top of an empty soft drink bottle, a pulse of sound travels down through the air in the bottle. At the moment the pulse reaches the bottom of the bottle, what is the correct description of the displacement of elements of air from their equilibrium positions and the pressure of the air at this point? A, the displacement and pressure are both at a maximum. B, the displacement and pressure are both at a minimum. Remember, there's a phase difference in here. The displacement is zero and the pressure is maximum, or the displacement is zero and the pressure is a minimum. Well, the fact that you have the bottom of the bottle, no air molecules can be displaced, so they are zero. So that leaves you C and D. But in this case, the pressure is a maximum, so the answer is C. The displacement is zero and the pressure is a maximum. Okay, and that's it for this section. We're going to go on with this speed of sound of waves. So we'll stop it here. Oops.